Actually, in this thesis, I'm using those telescopes to do this fast radio burst studies. And in the future, we also have bursts in Taiwan, which is my hometown, and also SKA, which is across Australia and South Africa. So in the future, we can detect more FRB and have a more general study of our FRB events. Okay, sorry. So I will start with my first project, which is the future constraints on dark matter with gravitational lens FRBs detected by bursts. So this work was submitted in APJ, which is last December. And this work is in collaboration with the following authors. So we know that dark stuff is cool, and astronomers like dark stuff, like dark matter, dark energy, or even there is a dark office in our institute. So about dark matter, I will talk about it in my first project. Actually, I will study about it. And dark energy, which will be covered in the next project. So fast radio burst actually is quite useful. It can be used as cosmic probe, like because of the high luminosity and short time scale of fast radio bursts. So like for dark matter in Munoz et al., they try to constrain dark matter using fast radio bursts. And for dark energy, Hashimoto et al. 2019A, he is also trying to constrain dark energy using fast radio bursts. So in first project, I will talk about dark matter. So how to constrain dark matter with using fast radio bursts? To be more specific, we are looking for gravitationally lensed FRBs, and later I will just call them lens FRBs. So I think most of you know what a lens galaxy has looked like. So lens galaxy, in this lab's image here, you can see the light from the galaxy is banded by the galaxy, maybe galaxy cluster. So from the image, you can see the light is actually banded. For fast radio burst, it's actually similar, but instead of galaxy cluster, it's lensed by primordial black holes, which is a hypothetical dark matter candidate. So here you can see the fast radio burst coming from here, and then later it is lensed by the plasma lens and also the gravitational lens, which is the PDH here. Instead of banding the light here, the fast radio burst signal is being separated into two bursts. So with a time delay of tau length. So this is how gravitationally lensed FRBs are detected. So help you to have more understanding how can gravitationally lensed FRBs help us to constrain dark matter. I will give you a story. So we can see so many kangaroos up on the Mount Stromo, right? So sometimes you also see something like this, which are the poop, or I would say the fetus. So imagine those kangaroos, they are invisible, like dark matter. So you can actually use these things up there to kind of estimate the number of kangaroos on our mountain. So this is similar to how you use lens FRB to estimate the number of dark matter in our universe. So actually in the past, there are like other constraints on dark matter, like previous microlensing surveys. They constrain the mass ranges of 10 to the -7 to 10 solar mass. Also CMB constraints larger than 100 solar mass. So for fast radio bursts, they are in milliseconds. It can be used to constrain the dark matter of in the form of primordial black holes of 10 to the 100 solar mass, which is this red region here. Unfortunately, like I've mentioned, that we have detected like 600 FRBs, but actually we haven't found one lens FRB yet. So the most successful survey in finding FRBs is the CHIME in Canada. So before CHIME, there were like less than 100 FRBs before. After CHIME begins its operation, it has detected more than 600 FRBs, which is a quick jump. However, most of them are not localized yet. So there are actually two challenges faced by CHIME. So the first one is it is lacking of localization capability because at this moment, it doesn't have outrigger yet. And then the second one is it doesn't have enough field of view or observational cadence to detect a large enough sample of FRBs. So here in this project, we are using BURST, which is a future, which is a telescope we're gonna build in Taiwan. So first, BURST 256, which is 25 times larger in the field of view than CHIME. It will help us to find lens FRBs in the future. And in the future, BURST 256 is evolving into BURST 2048, which we increase the number of antennas to make the sensitivity higher, so we can detect more FRBs in the future. So first, I will begin with the estimation and the constraints. Here in this first project, we are using a catalog from CHIME. So we are doing kind of empirical studies about this. In this catalog, we have about 500 sources of FRBs, and we have inferred redshift from Hashimoto et al. 2022, which they calculated the redshifts from the DEM. So here you can see the fluence distribution of fast radio bursts in this catalog. So we put the fluence threshold limit of our BURST 2048 here. So sources which is right in this figure is actually those sources that can be detected by BURST 2048 in this catalog. And later we plot the redshift distribution of this catalog of 100 sources. And also we scale with the difference in between BURST and CHIME of their field of view and also the sensitivity difference. So we get this figure right here. So we get a lensing probability integrated, or you can say the integrated optical depth equation from Munoz et al. 2016. So the NC in this equation is actually this redshift distribution here. So we are using this in this equation, and later we can calculate the lensing probability of it. So here is our results, which we show the number of expected detection of bursts, fast radio bursts by bursts per year. So here we show 4 different redshift beams, and you can see that the orange one is total detection of FRBs, and the red one is the one for lens FRBs in this parameter, which is the best parameter we can reach. And the blue one is the one for Munoz et al. Parameters. So for this BURST 2048, actually the lensing fraction from this work is about 1.5% per year, which is quite a lot. Using this result, actually, we can also do a future constraints on dark matter with bursts. So here I show you the dark matter fraction versus lensing mass plots. You can see that there are some past constraints from different surveys. And for bursts, actually, we have a better constraint in the lower mass region. And also, we cover the primordial black hole region here, which is quite good. And actually, that ends my first project. And coming up next will be my next project, which is constraints on cosmological parameters from dispersion measure and scattering of localized FRBs. So maybe you will know that the universe is expanding. So this Hubble-Lemaître law is kind of, they discovered this expanding facts and write this equation, which V is the recession velocity, H naught is the Hubble's constant, and D is the distance to the universe. So here, D is a key in this project. And V, you can see maybe the redshift in this project. And at the time, they're using the center candles to kind of prove this equation. So after that, we also know there is a fact that there is Hubble tension. So what is Hubble tension? Maybe you can take a look at this plot, although the letters is quite small, but actually these are surveys that is trying to calculate the exact number of Hubble's constant, which I show you in the Hubble's law equation. So actually you see there is 2 different values of Hubble's constant that they calculated. So this is kind of discrepancy between these 2 numbers, and we are not sure which one is correct. This creates a Hubble tension problem. And also in optical, so in this diagram here, some of the values are calculated by using type 1a supernova, which also, you know that some gentlemen here, including our Vice Chancellor, get Nobel Prize from it. So they calculated Hubble constants using type 1a supernova, but type 1a supernova is observed in optical. This may add some uncertainty to the intrinsic brightness of them, and also adding errors into the Hubble's constant maybe. So radio is free of dust extinction problem. So FRB may be quite useful for doing this kind of Hubble constant calculation in the future. So first, I need to tell you what is dispersion measure. So before FRB here reaches on the Earth, actually they are strongly affected by intervening medium like the IgM or CGM or even the Milky Way. This may sound like a bad thing because it is affecting, but actually it provides us a very useful information, which is dispersion measure. By using this dispersion measure, this is actually the D in that equation of Hubble's law. So we can use dispersion measure like it is a distant indicator for fast radio bursts. So how to do it? In McCurt et al. 2020, they actually model DM contribution in FRBs, which is shown by this equation. So DM MW is the DM from Milky Way, and DM IgM is from IgM, of course, and also IgH is from the intervening galaxy or halo. DMH is the key one, which is contributed from the host galaxy. So from Cordes et al., they say that the effects of intervening galaxy or halo is negligible in FRB's case. So this equation can actually simplify to this one, which later you can find that DMH is actually strongly depends on DM IgM because DM Milky Way, we kind of have a model for it. So by constraining DMH, actually we can get DM IgM, and DM IgM is actually related to H naught because this is a kind of distant indicator in this case. So actually we can use fast radio burst DM to calculate Hubble's constant. And actually some people have done this before, which like James et al., he calculated the number which is 73, and Zhao et al., he also calculated a number of 71.5. But these results, this result kind of favor the Hubble's constant for supernova type 1a. However, the error is quite large at this time. And also I need to mention that those results, they assume very much in the DMH because they kind of don't know what is going on in DMH. And so they put a lot of models in DMH. In this project, I'm trying to use a better method to constrain DMH so we can get a more accurate DMH, and thus we have a more accurate DM IgM and a more accurate Hubble's constant. So how I'm doing is I'm using scattering from FRBs. Just in case you don't know what is scattering, so here from this figure, you can see this feature is actually scattering based on a FRB signal. So when they are passing the maybe medium between us and the FRB, it will cause some scattering effects on them. And so for host galaxy, actually is dominated by scattering in FRBs. So you can say scattering is very important if we want to calculate a correct DMH. And in Cordes et al. 2022, they try to model DMH with scattering, and they try to estimate a more accurate redshift with them. So in this project, instead of estimating redshift, we are using known redshifts, and we try to constrain a better DMH, and we can get a better DM IgM and a better Hubble's constant. To get known redshifts, we are using the survey which is called SCAP, because SCAP is actually the best telescope in terms of localizing FRBs nowadays. So we can get redshift from there, and most of them are spec C. In fact, more than 60% of the FRBs are observed up to date are actually localized by SCAP. So it will be very useful to use the data. So in this project, Yan et al., which is one of my collaborators, is trying to constrain the Hubble's constant from scattering of FRBs. And hold that out, which is me. I'm trying to do cosmological parameters with using this Hubble's constant and also scattering. And also in the future, I can extend it to CRAFT, which is a project in SCAP. They are trying to detect like 1 FRB per month. So if we get a larger number of FRBs which are localized, we can get a more accurate number of Hubble's constant. That's the project 2. Project 3 is about searching for FRBs from globular clusters. So the origin of FRB, actually, I mentioned there are so many models, but actually there's one model, which is the magneta. So magneta is a type of neutron star, which is with a very extremely powerful magnetic field. This kind of objects, there are many papers saying FRBs are actually coming from them. And we actually have one FRB, which is localized to one of the magneta in our universe. So you can see that this is one of the maybe most favorable candidate of FRB origin. However, which is last year, they have detected a repeating fast radio burst, which is localized to globular cluster. This is very strange. I will tell you why this is strange. So magneta, just to tell you that they are actually a young population formed in a core collapse supernova. But globular cluster, we can call it GC, instead they are hosting old stellar populations in our universe. So one is young, but one is old. What is happening? We don't know. Fast radio bursts. So some of them are coming from young population, but some of them are coming from old population. Is it what you mean? Actually, in this paper, they are suggesting that this may come from a product of magneta, which is formed by blah, 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 but this is just some words from this paper and just a model. And in fact, we only detected like just one FRB from GC. So we don't know if it's true or not. So maybe we are asking, are there more FRBs coming from GCs? So in this project, I'm trying to prove that. And actually there are 2 directions in this project. So the first one is I'm trying to search for giant pulses from millisecond pulses in globular cluster using meerkat data. So just to let you know, pulsars, they are actually highly magnetized rotating neutron star that emits radio pulses. Kind of familiar, right? Because magnetism is something similar. And millisecond pulsars, they're actually the millisecond version of pulsars. So from this figure right here, you can see that this FRB was the FRB I'm talking about in the last slide, which localized in a globular cluster. And you can see giant pulses from pulsars are actually here. So the only difference between them, you can say, is just the luminosity difference. So fast radio bursts, they are much brighter, like in 4 to 6 order difference in the luminosity. And actually, millisecond pulses, they are quite common in globular clusters. So trying to find giant pulses from millisecond pulses in globular clusters may link FRBs with them. So this is kind of interesting. And to mention that millisecond pulses is also a very kind of interesting event in our universe. We don't know much about them. So if we don't find FRB from them, finding millisecond pulses, giant pulses from millisecond pulsar is also interesting. So how do we do it? We are using meerkat data, which locates in South Africa. It has a very high sensitivity, which is 10 Jansky. And actually we have connection with Matthew and Chris from Swinburne. So we can kind of get meerkat data on globular clusters. So trying to find giant pulses or even FRBs from them will be this project I will do. And the second direction would be I'm trying to find FRBs from GCs using Parkes data. So from this paper, Kramer et al. 2022, they have so this is after the paper, which is about localized FRB from globular cluster. they try to estimate the number of FRB events from all the global clusters in our universe. And in this paper, they are actually saying M87 is the best galaxy for finding FRBs, but M87 is too north. So in this paper, SAN A is the best candidate in the southern sky, which we can use our telescopes to detect it. Also in Chen et al. 2022, they are saying that there is possible connection between ultra luminous X-ray bursts and repeating FRBs in SAN A. So actually they have detected some ultra luminous X-ray bursts from it. And they are saying that they have connection. Maybe this will be the counterparts of FRBs. So in this direction too, I'm trying to use CryoPath, which is a new instrument which will be installed in Parkes, and it will be 2 times more sensitive than CHIME, and it will be less competitive than ESCAPE, so I need to worry less about it. And also it has a large enough field of view, which is 1.9 square degree. And for this project, I'm collaborating with Ron and Clancy, who are from CSIRO and Curtin. We're trying to maybe write a proposal or do science commissioning with Parkes data. The 2 globular clusters, or I would say galaxies, we are targeting. The first one will be SAN A, which I mentioned. However, it is kind of bright in radio due to the supermassive black hole at the center. So we are proposing a backup plan, which is NGC 253. In fact, it is closer and is not affecting by radio. So that ends our project 3, and I will come to project 4. Project 4 will be searching for counterparts for FRBs. So far, there are only 2 counterparts for FRBs we have detected, which is X-ray and another one will be gamma ray. And actually many FRB models from the FRB theory catalog, they kind of predict that there are multi-wavelength counterparts for FRBs, but we haven't detected them yet. And actually most of them includes like optical or infrared counterparts. So what's so important about detecting counterparts for FRBs? This actually provides us information about the physical processes. So this is very important. Actually, this is kind of similar to the case of gamma ray bursts. So gamma ray bursts, we detected like 40 years or 50 years ago. We only detected its counterpart after 24 years by this paper. And actually this detection, this optical counterpart is very important because it is a strong evidence for the impulsive fireball model, which only proved this after these detections. So for FRB, we are doing something similar. Like in this project, I'm trying to join the deeper, wider, faster program in Swinburne. So they are doing kind of simultaneous observation of FRBs using different wavelength, different telescopes. So I will join this. Also, I'm trying to write a proposal to FAST, and we actually, some of our collaborators have connection to Tomo Egoze telescope in Japan. So both of these are in the northern hemisphere. So we can do simultaneous observation in the optical wavelength to see if there's any counterparts. So that ends our project 4. So here comes to some of the potential risks in my projects. So I would say for the project 1 and project 2, they are less risky because project 1 is almost finished. I just submitted. And also project 2 is about calculation and modeling. So I would say it is also less risky. For project 3, I have 2 directions. For the first one, it's less risky because we have kind of data from Meerkat already. But for the direction 2, it's actually quite risky because we may need to face like proposal fail or even non-detection. So for some solution, some solutions for them, maybe we can kind of switch telescopes, or it would be great even writing an upper limit paper, I would say. For project 4 is, I think, the most risky project in my thesis. And actually it is a high risk, high return paper because I don't want to spend like 24 years in my PhD, right? Like a gamma ray burst case. So, but if you detect it, it will work for nature, I would say. So this will be the most risky one in my thesis. And I will also show you my timeline for my PhD. So for the first year, which is currently, actually project one, I just submitted the paper and I presented it at the FRB conference in Taiwan, which just happened last month. And actually I got a prize, which is the best oral presentation from it. And for project three, I'm also doing it in the first half, which is the meerkat data analysis, which I hope I can do it. And I also hope I can visit Swinburne at some time in 2023. And I will also try to estimate the GC's events rates with prior path. That's what I want to do this year. And also some conferences, of course. For the second year, I'm doing more focus on the project two, which might be my paper 4. And if I finish this, I can extend it with the crab data in paper 5. And if there's time, I can do my project 4, which, yeah, the counterparts one, and also some conferences in the second year. For the third year, which is close to my end on my PhD, so I would do some other interesting projects if possible. And also I will start writing my thesis. And this will also be my buffer time if anything goes wrong, like if I don't detect anything, maybe I will do it this year. So here comes to my summary. Actually, I don't know what to put here, so I just put the project titles here. And actually, I have a take-home message here. So the study of FRBs is actually still in its early stage. So there's much to be learned from them. So if you are interested, please join us and unravel their secrets. Thank you.
Thanks for that presentation, Simon. Really
Thank
good.
you.
So I'll open up the floor to questions. If anyone has any questions, both in the room and online, we've got a couple. So Marcy first.
Hi, really nice talk and very interesting this proposal. Hopefully you get lots of good signals, good noise. Best of luck. So I just wanted to ask 2 questions. So one question was because I'm not very familiar with FRBs. So when you so what kind of data are you what kind of so if you have a data, what kind of parameters do you use to identify whether this is a fast radio burst? That's my first question. And also the second question is you connected FRBs to dark matter, and I was wondering what's the justification for being able to use FRBs to measure the dark?
So your first question is how do we?
What does the FRB look like in terms of data?
In terms of data.
Yeah.
So I don't know if I have some figure here. Let me check. Sorry. I might want to show you the. So this is the plot of the one of the FRB. People can see it. So for this line here, is actually the radio signal from FRB. So here I am plotting the frequency versus time. And why this is tilted is because of the DM I mentioned. So they actually the signal arrive in at different time with delays due to the DM thing. So that how FRB is look like in the radio data. Does it answer your question?
Okay.
Yeah. So for the second question, what was it? Sorry.
Well, second question is how do you connect FRBs to dark matter? You said there's not much agreement from the origin of FRBs, so I was wondering how do you connect? How do you justify using FRBs to measure dark matter?
So that was the first project I was talking about. So actually our way was to just try to calculate the dark matter fraction of dark using FRBs. So you are saying how am I going to connect them together? But
yeah, so I don't know a lot about FRBs, so maybe that's why I'm confused about it. But I was wondering, so you what's the origin of FRBs such that we're able to use FRBs to measure dark matter?
So to me, actually, even if we don't understand the origin of FRBs, it would be still useful for doing dark matter constraint because due to its luminosity and short time scale, it's kind of like transients. So actually in the past, we also use different transients for doing this kind of dark matter constraint. So that's something I'm trying to do in project 1. So we are just trying to calculate the dark matter fraction by using the future constraint of burst in that observation. Yeah, I need to do some modeling about it. And actually my project 1 is based on that Munoz et al. Paper. It's trying to assume dark matter is kind of composed by compact objects like primordial black holes. And primordial black holes that they may trying to lens, FRBs may lens by primordial black holes. By doing this, by observing this, maybe we can have a hint of how many dark matters are there.
Cool, good bunch. I think there was one at the back first.
Those are 2 questions.
Yeah.
The first one is, by how many chance you think we can detect?
Right.
And the second one is that starting with that.
Right.
Sorry. The uncertainty of the concept of the use some uncertainty distance
Sorry, just because people online didn't hear the question. The first part was about the percentage chances of detections of FRBs
In globular clusters.
in globular clusters specifically.
Okay, so for the first question, like I mentioned, we have detected like 600 FRBs from, all the FRBs, but actually there is only 1 FRB from globular clusters. So I would say actually this is very risky and the chance may be very little. But actually in their case, they're actually detecting extragalactic FRBs. So in my opinion, if we want to detect maybe globular cluster FRBs, maybe trying to detect the closer one will be better. And also for the southern sky, is less study than the northern sky in terms of FRBs. So doing this in the southern skies will be, I think, better chance maybe.
And as for the second part of the question, it was looking at the uncertainties in distances and how that plays a role with the Hubble constant calculation. Is that? Yeah.
So for this question, you are saying how the counterparts or how the origin is affecting that uncertainty?
we don't know, and from slide you see that
So I'm not sure about the concept, but really matters here. But so for the current situation, we have like only 600 FRB detected. That makes the uncertainty so big, like for the Hubble's constant. So in the future, we are detecting maybe after SK, we have more than 10,000 per year, and that will actually strongly kind of constrain our Hubble's constant. So it will become more accurate in that case. I don't know if this is the answer.
Had a question here at the front.
A related question,
Right.
I guess. Thank you. That was a brilliant talk.
Thank you.
So implicit to your definition of the dispersion measure, I guess you're assuming that in the underlying mechanism, that all of the broadband emission is simultaneous, that you're not getting a lag for different frequencies, and that all of the dispersion is due to the so I guess I'm just curious about the localizations that were done with the ASCAP FRPs, were the distances consistent with what you got from the dispersion measures?
This is a good question, and actually it's kind of difficult. So there are people trying to calculate redshift from dispersion measure, and I would say actually the uncertainty is quite large instead of using spec-C from the localized host galaxy. So I'm not quite sure if they can relate, but in order to get a larger sample, using redshift from DM will be maybe the best thing we can do now. Yeah, like in my first project, I'm trying to estimate based on the infer redshift from DM. Yeah.
When you say localized, do you mean a position or do you mean an association with the back of the galaxy?
Yeah,
I mean,
I'm saying that.
localization could just mean measuring the position on the sky. It doesn't necessarily mean that there's a galaxy at that.
Sorry.
When you say localized, the ones ASCAP has been localizing FRPs.
Yeah.
Does that mean just measuring an accurate position?
Uh,
Or does it actually mean measuring an accurate position and at that position is a galaxy?
yeah, that is actually, I would say the first case because they have interferometry in SCAP. And also, if we get the first case, I would say the second case is also kind of possible because if we get a correct localization for the burst, and then we can kind of relate it with, maybe localize it with a host galaxy which is very close to it. And then later we are using maybe telescope in Chile to get the optical follow-up observation to get a redshift. Yeah, does that answer your question?
We have a question. Yes, sorry.
I'll start off by saying I am sure that observation.
Yeah.
But do we have an understanding for how many versus regular repeating events?
You mean how many repeaters?
Yes.
So repeaters, are you talking about the subburst or just one?
We're talking FRB goes on, goes off like the Wi-Fi.
Yeah. So for so actually for the, repeating events is actually much less than those non-repeating one, which we have observed nowadays. But for the subburst, like the FAST telescope in China, they're actually detecting many subbursts from a same FRB event. So it would be like 600 events from that. But for repeating, single events is just like 20 something out of 600. Yeah, something like that, which is a very small portion.
Jonah had his hand up first. So.
Yeah, very cool. Lots of good ambitious goals, and so we should invest with them. In particular, with the fourth one,
right.
It's a bit. To me, it sounds very hard because we don't looking for that point. Yeah. So, do you have any kind of ideas of what you're searching for?
Yeah, actually. So I mentioned that I might write a proposal to FAST. Actually, I kind of want to relate it with the project tree. Actually, I'm trying to propose targeting global cluster with FAST, maybe the Northern global cluster, So trying to find counterparts from this kind of events may be very interesting, and that's what I want to do.
To show me the burst before and has, what would you expect gravitational observation?
You mean repeating and gravitational lens?
So what would it, when we look at gravitational lens galaxies,
right?
All figured out. So like, what is a gravitational lens?
Yeah. So, sorry, I'm trying to find it. So from this plot right here, I was showing that lens FRB are actually lens by plasma lens and also the primordial black hole, which is a gravitational lens. So in terms of the signal, they will be separated due to the lensing effects. So you would see two signals instead of just one, which, yeah. And there is a time delay of tau length in this case. So that's how we see a signal. But if you are asking how am I going to differentiate this from repeating bursts, sorry, I don't have an answer on this.
In the middle, yeah.
Questions. The first one is, why do you anticipate that the lens FRB is lensed by the PBH? So are there any physical connections? So this is the first question. And the second one is, what is the advantage to use the lens FRB that we have lenses because they are way more than the lenses that we use.
Right. That's a good question. So from this plots right here, you can see that this region missing, even though we have so many surveys, maybe using Galaxy to do dark matter constraint. So actually, in terms of the time scale, FRB is very useful for doing this constraint. Let me show you an equation. So by this equation, maybe not this equation, but in a more complicated equation, you will see the time scale really matters in terms of constraining different mass ranges. So FRB for millisecond or even nanosecond will be in this region, which is the primordial black holes candidate. I mean the past paper, they are saying this mass region will be primordial black holes for one of the candidates. So that's answering your question.
So the advantage of that is
Right.
No, it probes the power from that. Yeah, the missing bits of the doesn't tell you anything about individual source.
Sorry, what was your second question?
well, the second question is what is the advantage of using less FRB rather than just competence?
Oh, so I hope I answered.
Yeah.
Matthew just online asked a follow-up question to that, asking, but FRBs have time structure on millisecond time scales, so how do you separate that? I'm guessing that was from separating the structure of the millisecond timescales from the actual structure that you see from the primary black hole. Is that where you, yeah, from lensing?
Yeah. This is difficult. I'm not sure if I have an answer now.
You're trying to measure a delay.
Right.
Is that intrinsic to the structure of a single pulse?
So you've taken a single burst, different structure, and structure. You measure delay. You lens events. That delay tells you about power spectrum mass that causes
If you see a double pulse, you don't know if it's one FRB that is intrinsically a double pulse, or if it is two parts around the.
well, I mean, at some level, that's a big length, right? Separate more pulse width.
Yeah. So in case Matthew didn't hear that from the audience, the answer was you would see the delay is the main property that you want to look for, regardless of the millisecond structure. If it's delayed, that's the main property you see from the primordial black hole lensing. Is there any other questions at the back? We had one more question.
I guess this is sort of a question about rating. From what I understand, the number of detections hasn't increased. I guess my question is just how exactly do you, based on, this is just 5%, right? That the rates you expect to be able to find, I guess, sources of rates as well as the program they've been operating for now? Survey strategy is also relatively, I would say that's what it's extremely targeted in terms of.
Yep. So in terms of the event rates for Chime, actually in their first paper, they are estimating they can detect like 1,000 FRBs per year. And so far it's not up to 1,000, we will know that. And actually, I would say we'll see, because I think the next Chime data release will be 2 months later or next month. And we will see if there are more fast radio bursts from that catalog. And actually, I think this month they just released a catalog with repeating bursts, which they found 24 repeating bursts from Chime. So that actually increased a lot in terms of the number of repeating bursts, which I say it was just like 20 something in the past. And I think, and in the future, I think there are more telescopes like currently just operated, which is the DSA in California. They are also detecting many fast radio bursts in just 1 month. Like I think more than 10 for localized fast radio bursts. And not to mention SKA in the future, they are estimating 10,000 per year, which are quite a lot. And for global cluster FRBs is, of course, is very risky, I would say. But we don't know if we can really detect it. But we don't know. I mean, we'll see after observing so many fast radio bursts in the future. Maybe we can detect one will be enough, I think.
Were there any other questions in the room? Also online, really any other questions? I know we've gone a bit over time with questions, but I'm sure if anyone else has any questions, they can email Simon at some point.
Yeah,
I
thank you
imagine.
very much.
So I guess we'll probably leave it there. So once again, let's just thank Simon for his talk. And, yeah, see you later.
Thank you.
Fantastic, thanks.
Thanks.